Section 6.8 Introducing the equilibrium constant for a mixture of ideal gases. You're looking at a very general chemical equation from A plus B to X plus Y. Nu A, nu B, nu X, nu Y are the coefficients. The Gibbs energy change of this reaction is the Gibbs energy of the final state minus the Gibbs energy of the initial state. Therefore, we write this Gibbs energy of reaction as the sum of the Gibbs energy of formation of all products minus the Gibbs energy of formation of all reactants. Remember, when we are talking about Gibbs energy of formation, we use pure elements in their most stable state of aggregation at 1 bar and 298 K as zero references. Now let's look at this equation. We can rewrite this part in this form. Pay attention to the difference. Over here, there's no superscript. Over here, there's a superscript not. So what's the difference? Over here, for products, this Px and Py do not have to be 1 bar. Over here, Px and Py are exactly 1 bar, the standard state. However, there's a difference. Again, over here, the pressure of X is Px. Therefore, we need to include some correction here. This nu X is the coefficient, and over here, this RT ln logarithm of the ratio of pressure tells us the difference between the Gibbs energies when the pressure is Px versus the pressure of 1 bar. So we do the same for Y, right? So therefore, this term is simply this term at the standard state plus the corrections here. This term, non-standard state, is equal to this term, standard state, plus the correction here and here. Because of this negative sign, we have a negative sign here, negative sign here, and negative sign here. This is important because we are about to introduce the equilibrium constant for the reaction. This is delta G of R, and then if we combine these two terms, that's the delta G of R in the standard state. We call this standard Gibbs energy of reaction. And over here, if we put all these terms together, it's actually RT times the logarithm of Q sub P. Right? Again, over here, this is Gibbs energy of reaction. It goes here. This is Gibbs energy of reaction in a standard state. These two terms. Finally, this one, RT times the logarithm of Q sub P. Q sub P is the reaction quotient. So this term is the sum of these four terms, including products and reactants. But remember, when we do logarithm, this nu X, when we put this inside the logarithm, it becomes logarithm of Px over P naught to the power of nu X. And this negative sign over here tells you we need to put this on the bottom in a fraction. Therefore, this Q sub P is equal to Px over P naught to the power of nu X. This is for X, this is for Y. Products on top, reactants on the bottom. We take care of the coefficients. And also, every single Px, Py, Pa, Pb should be divided by P naught. Therefore, every single term is unitless. Q sub P is unitless. Because of this P naught being used as a reference, Q sub P is called the reaction quotient of pressures. When the reaction reaches equilibrium, again, at equilibrium, that means the Gibbs energy of the reaction reaches the minimum. There's no longer any change. It can no longer change, and then we say delta G sub R is 0. When delta G sub R is 0, we know this part, this sum, is 0. Over here. And also, when the reaction reaches equilibrium, this Q sub P at equilibrium, we call that equilibrium constant. The notation is K sub P. So K sub P is Q sub P at equilibrium, and it's called the equilibrium constant of pressures. So the formula of K sub P is almost exactly same as Q sub P, except that we need to put equilibrium in the subscript to emphasize that K sub P is Q sub P at equilibrium.